section 2.2, polynomial functions of a higher degree. Basically, if you keep in mind that we just covered the quadratic functions, which are also considered polynomials, we're now going to take a look at what happens when polynomials have a variable that's x to the power of 3 or higher. I want to make sure that you can look at the equations for polynomials and give some good guidelines on what it would look like if you were to sketch it. Vocabulary I want you to be watching out for. Watch out for the leading coefficient test, for describing end behavior, and for something called turning points. This will be part of our dialogue as we go through this next unit of material. So first of all, I wanted to start with checking to see what you remember. So I'm giving you a question. This one is a random polynomial, and I want you to try to describe what the zeros will be, the end behavior, and the turning points. And so please just take a look at that, stop the video, give it a try, give a good sketch, and then you can start once again. Once you have your answer, we'll hang on to that and we'll look at it a little bit later once we've had a chance to review some of the important topics that we need to cover. So when we're talking about polynomial functions, there are a couple of definitions I want to start out with. In other words, to help us understand what they actually look like. Here are a couple of polynomials. And if you were to look at them and describe them, there are a couple of key words that we need to use. First of all, polynomial functions are continuous and smooth. Now, in some ways, it's easier to understand what we mean by continuous and smooth by understanding what they do not mean. So if we look, first of all, at the continuous side, something that is not continuous would be an example like this one. Now, this is a piecewise defined function. He is a function. But because if you were a tiny little insect traveling along this function, all along here, you'd get to a spot where you'd have to make a jump and another jump to get back into the function again. So we say that this is not continuous. This is not a polynomial function. Functions with graphs that are not smooth. So let's look at what it means when something is not smooth. What you have is an abrupt turn, a corner. And we say that this is not smooth. And so this is not considered a polynomial function. It is also probably a piecewise defined function. You can tell you have a linear and a trig function, but it is not considered a polynomial. So once again, polynomial functions are continuous and smooth. Now, we need to get a little more specific about what they look like, and one of the best ways we have of describing these graphs is to look at the way they behave at the end of the graph. The cool thing is that polynomials will always have end behavior that continues without limit. They either rise or they fall on the edges of these polynomials. So in order to understand it, and you should remember this from last year, we call it the leading coefficient test. You always look for the leading coefficient in an equation. And then based on whether it is even or odd, as in terms of the variable, or whether it is positive or negative, you'll be able to predict what the end behavior of the graph will look like. Now, in order to keep it simple, we're just going to depend on some graphs that we actually know. We're going to use x to the power of 3 for the odd functions when the degree is odd. And we're going to use, so we'll get to the even ones in a moment. But first, let's describe what we see. Basically, you can see it's falling and it's rising, but we have a very particular way of describing that. We say that as x approaches infinity, y also approaches positive infinity. As x approaches negative infinity, y approaches negative infinity. So then when we turn it around and we have x to the power of 3, but it is negative, we're going to use its end behavior to describe negative odd degrees. So when x tends towards infinity, then the y goes towards negative infinity. As x approaches negative infinity, y approaches infinity. So these are standard things. I'm not expecting you to memorize this stuff. I want you to remember your graphs that you know already, and then remember the language that we're using for describing them. The second set of functions will be functions which are considered even, and we're going to use x to the power of 2 for this one, positive and negative. And so we use the same descriptive language to describe it, to show that it's rising on both sides. The y is approaching infinity. And when it is a negative behavior, we'll show that the y's are going down on both sides, approaching negative infinity. Okay, so the trick to keep this simple is to use a graph that you know of so that you can memorize it. I don't want you to memorize that language. I want you to be able to imagine what it would look like. So we'll try this one. So our leading coefficient in the first one is a negative odd degree, which means it's going to behave like a negative x to the power of 3. And that means, if you look at it, that it's going to go towards positive infinity on this side. It's rising and it's falling. And we describe that using the language we had from before, keeping in mind that this is like negative x to the power of 3. Take a look at the next one. Your leading coefficient is x to the power of 4, which is even and positive. And so it will behave like the x squared function does, rising on both sides. And so we describe it using this manner. The last one, just be careful. It does have the leading coefficient hiding in the center. It's an even variable or even degree, but it is a negative version this time. So the two sides will fall on both sides. And sure enough, here is our graph, and we describe the behavior in this way. By the way, I didn't explain that in the first one, but basically what I did was took a screenshot of what these functions look like. So you can see that it's true. The end behavior is something that we can predict. All right, when we're looking at polynomial functions, we also consider the zeros, which you should be comfortable with, the places it crosses the axis, x-axis, and something called turning points. So here's a standard polynomial. You can see that it's got the pink ones show where the actual zeros are. And then the things called a turning point are the blue ones, where the graph changes direction. Now, the cool thing about it is once you know the degree of your function, you can make a prediction about these two things. It will have the same number of zeros, except, well, it will have the same number of zeros, but keep in mind that some of these may be imaginary. So it's basically, it can have up to that amount of x-intercepts, but all of them will be zeros. And then at the most, it'll have n minus 1 turning points. If you look back at the one we had just a moment ago, this one has 4 intercepts and 3 turning points. So that's one extra point that you need to watch for. And you're going to see it when you graph this guy. Now, if you look at him, you can tell he's going to have zeros at 0, 2, and negative 1. Now, we've got this squared function here, so essentially that means that the 2 could be twice. So we're going to have 0, 2, 2, negative 1. Now, we can also tell, because there is 1x here, there are 2 x's here, and 1 here, that our function is going to be an even, and it's positive. So it's going to rise on the left and rise on the right. So let's take a look at what we see. Here's our graph. Okay, it's rising on the left, rising on the right. It has an intercept at 0, one at 2, and one at negative 2. Now, it's done a curious thing though, because at 2, it bounced away and went back upwards. And it turns out this is a rule. If you have anything that is of a more than 1, so an odd degree will be fine, it goes through and touches it, but if it's an even degree, the graph will simply bounce. It'll touch the axis, but not go through it. So, number 2, let's sketch the following function, and we need to include its zeros, its end behavior, and its turning points. Okay, it's a degree of 3, so it could have a potential of 3 zeros. Its end behavior is going to be like x to the power of 3, so it's going to fall on the left and rise on the right. Then we need to factor it. In order to factor it, we're going to need to take out an x. And when we do, if we pull out an x, we should have a perfect square, sure enough. So we have x and x minus 6 and x minus 6. So we're going to have an intercept at 0. We're going to bounce at 6. We're going to rise on the left and rise on the right. Now I want you to stop the video with that information and do your best to create a sketch of all that with that information. And then let's see if I actually put it here. Yep, here it is. So you can see it's going through 0, it's bouncing at 6, and it's falling on the left and rising on the right. Okay, now this last one is more of an algebraic style question. It's, can you find the polynomial it came from if these are the zeros? So you had x equal to -1/2 and x equal to 3 twice. So basically we're asking you to go backwards now. If it was x equal to 3, then x minus 3 was one of the factors, and so you'd have that twice. And then x plus 1/2 equal to 0 would be one of the other ones. And because I don't like a fraction, I multiplied everything by 2. And all I'm doing from there is just going ahead and expanding things and simplifying. And what I find out is that the polynomial in its original form that had these zeros would look like the following. Okay, so let's look at the starter question one more time before you leave it. And so we'll go here. Now we're supposed to sketch, this guy's supposed to include the zeros. If you look at it, you're going to have 4 zeros, 3 turning points. Because it's a negative even function, we're going to have it falling on the left and falling on the right. And we were supposed to get the zeros out. Now that's a little bit tricky. I don't remember that I actually included that in the solutions that I had, but you would have had to make it equal to 0. Would have had to multiply everybody by 4 to get rid of these fractions and factor out an x squared. And then, you get a fairly simple looking thing. And you should be finding that you have a 0 at 0 and you have 1 at 3. And in fact, 2 of them at 0 and 2 of them at 3. And you can see the end behavior is following on both sides. Alrighty? So once again, if you have any questions about this, make sure as you go through your homework that you circle it and bring your questions to class. Take care, everyone.